Okay, good morning, everybody. So it's my pleasure to share this second seminar by Professor Scott Milner. Not all of you might have been there when Scott gave his first seminar, so let me briefly introduce him. So Scott received his PhD from Harvard University in theoretical condensed matter physics. And after two postdoctoral positions at ExxonMobil and Bell Labs, if I recall correctly, he was a research physicist at Exxon for about 20 years before joining the Department of Chemical Engineering as a faculty member, and he still holds the professorship position there, and he has been there since 2008, if I recall correctly. So Scott is very well known in the field of polymer physics. He had many important contributions. His early career was marked by, I would say, polymers at interfaces, polymer brushes, mesophases, nonlinear flow in polymer solutions. And if I recall correctly, you also received the Dillon Medal of APS for this work.
That was a long time ago.
That was a long time ago. Recent activities involve, well, entanglements, polymer crystallization, glass transition, semiconducting polymers. And now he returns to, well, I think an old and important topic, predicting miscibility using simulation. So we are very much looking forward to your talk.
Thank you, Jörg, for that kind introduction. Can everybody hear me in the back? I hope this microphone is working for the Zoom. What do I use to advance the slides? The keyboard or? Yeah, okay. All right. So, so as Jörg said, what I want to tell you about is work that I've been doing recently. This is in the past 4 years, 5 years, something like that, to use simulations to predict miscibility of fluids and fluids including polymers. And so there's a long list of contributors here, many of whom I am very proud to say are research undergraduates. So I will tell you in this talk sort of a succession of ideas that we had for addressing the challenge of using simulations to tell you about whether two fluids, how strong a tendency they have to demix or potentially to mix. And try to, one of the messages, of course, is, what are the methods that we use for that? But another part of the story is, how did this sequence of ideas come about? And I think somehow it's illustrative to look back and think, well, how did I get that idea in the first place? And how did I get the next idea and so forth? And I think that's an interesting story here that I'll try to emphasize. So to begin with, just to tell you things that you all know and that should make you feel comfortable about miscibility. So if you knew the mixing free energy is a function of composition, then you could predict whether things would mix or not. You can calculate the phase diagram and so forth. So, mixing free energy governs miscibility. Simple models of mixing, of course, make various approximations about what that mixing free energy might look like, and the one archetypical case is the so-called regular solution, where you have a mixture of molecules that are similar but not identical. So maybe they're the same size and shape roughly, but they have a little bit different interaction. So that we can think of it as a perturbation of an ideal solution, roughly speaking. And so one can write down a free energy that has various names associated with it, depending on whether you're a chemist or a physicist or what have you. But basically, the idea that if I randomly place these molecules, in the liquid or randomly choose their identity, that there will be some probability of unlike species being next to each other, which, if the interactions between them are weak, is not very much perturbed from what it was when it was an ideal solution, therefore that it's still pretty randomly mixed. And then, roughly speaking, that probability of unlike species being next to each other is, x1 minus x, phi1 minus phi, that sort of thing. And then there'll be some coefficient that sits in front of that that tells you what the free energy cost of that unlike interaction is. And from this, you can compute a phase diagram and so on. And you need to know what that number is for a given liquid to know, where you are in the phase diagram. And so that's the challenge, is to know what chi is. The same thing's written in polymer blends. The difference being, of course, that the translational entropy is relatively weak on a per monomer basis, since there's only one translational degree of freedom per chain, but every bead has some chance, every monomer has some chance of sitting next to an unlike monomer. So the ideal mixing term has a 1 over n in front of it, where n is the number of monomers, and that makes polymers hard to mix, right? It makes the critical point of mixing two chains of equal length is, a chi of order 1 over n, not of order 1. Because any piddly little repulsive interaction per monomer will add up to make it worthwhile to move, one kind of polymer to the left side of the box and the other kind of polymer to the right side of the box. So it's actually pretty hard to make miscible blends. There are examples in commercial practice of miscible blends, not many. One of them is this product called Noril, which is a mixture of those two polymers. And the nice thing about a miscible blend is that you can continuously tune parameters. And in the case of Noril, one of the things you can tune is the glass transition temperature and therefore the stiffness of the material. And so it's a very nice commercial product that made GE a lot of money to prepare, just by blending a whole family of materials with different stiffnesses. As I said, mostly polymers can't be mixed. When you make them long enough, they'll demix. And then chi still matters because it determines the interfacial width. And the simple story of that, I mean, the calculation of this, dates back to Helfand and Tagami in the mid-70s. But the simple story of this is which is all I remember about this whenever I need it, is if you want to predict the width of this thing, you should consider an initially sharp interface and imagine the random walk that a segment of a long chain might try to make onto the other side of the barrier. And every step it takes costs it chi, but it's willing to spend something like KT to make this fluctuation. And so how large a little excursion can it make? Such that cost of that is KT determines the number of monomers that might be apt to visit the other side by a thermal fluctuation. And then, that gives you the scaling for the width of the interface, which is that it goes like 1 over the square root of chi, which is consistent with the careful calculation. So that means then that if you make things a lot immiscible, then they have very sharp interfaces. But if they only have kind of moderate values of chi, so that it takes a fairly large molecular weight to make them demix, then the interface can be somewhat broad. And that too is useful because in immiscible blends like impact toughened polystyrene, where you've suspended a bunch of little rubbery droplets in a polystyrene matrix, you need those interfaces to be broad enough that they entangle. Otherwise, if they're too sharp, then you won't get the sort of interlocking of the two materials. And then when you try to drive a crack through the thing because you dropped your phone on the floor, then the rubber will fail. The interface between the rubber and the glassy plastic will fail. So you need to know roughly what that interfacial width is to know whether or not the rubber toughening will work. Well, okay, so you need chi, and measuring and predicting chi is hard. It's pain. Predicting it historically is particularly hard, and it's not like people haven't tried. So one area where it works pretty well to predict chi in terms of solubility parameters is for polyolefins. And polyolefins are kind of boring, and I should know because I worked for ExxonMobil for 20 years. and that's the only kind of polymer they make mostly. They're boring in the sense that they're nonpolar. They don't differ very much. They differ a little bit in their index of refraction or, or their polarizability. And those small differences drive the demixing. And because they're so similar, in many cases, you can predict their chi parameter on a phenomenological basis of like prefers like. And so the chi winds up being proportional to the difference in solubility parameters squared, or equivalently the difference in Hammaker constants, the difference in monomer polarizabilities squared, and that's rationalizable. I mean, and so beautiful work by Gressley and coworkers shows that for a whole series of random copolymers in which you vary systematically the content of hexene or something, that you can predict windows of miscibility. Works great. More ambitious efforts to predict the miscibility of anything with anything based on what kind of groups it has, the chief system of which is Hansen solubility parameters, basically don't work. That's perhaps a somewhat heretical statement, but they don't, and the reason that they don't is because everything in that formalism is based on like prefers like, and things having a net interaction, which is the sum of squares of differences of something, and not all interactions are like that. In particular, hydrogen bonding is not like that, because a hydrogen bond interaction is asymmetric. There's a donor and there's an acceptor, and molecules can be donors in the sense that they have an acidic proton that's just looking for a negative charge to stick to, but not themselves have an isolated, strong, locally negative site. Something like a polymer with a chloride on it, which will tend to pull electrons off the proton, is looking for a concentrated ether oxygen or carbonyl oxygen to stick to, and other monomers which have that don't have an acidic proton. And so it's possible to make miscible blends based on that strategy, and indeed there's a book about that, which is by two professors now emeritus from Penn State, which in very physical terms describes the kinds of blends that you can make that way. Measuring chi is something that people have worked really hard to do, and it's tedious and difficult, but can be done in basically three ways. Either you measure the cloud point and fit a phase diagram to it and infer chi, or you can, and this is the sort of gold standard, you make a deuterated labeled system in which you're able to do neutron scattering and measure fluctuations in the miscible regime. So you need chains short enough that they mix, and then you fit that to the random phase approximation, which is the theory of fluctuations of something that's thinking about demixing but hasn't quite done so. Or you can, when things are actually immiscible, you can measure by reflectivity the thickness of the interface between the two, which if it were perfectly sharp would give you very strong Fresnel reflections, and if it's not quite so sharp, give you somewhat damped reflections and so forth. And so that's hard to do because, well, because reflectivity is hard, but also it's hard to make a really flat interface that doesn't have a bunch of crappy wiggles on it that have nothing to do with the interfacial width you're trying to measure. So those are the ways experimentally. So what about simulation? Well, so when I started thinking about this, I was learning, I mean, I should say I didn't do simulations before I went to Penn State. I actually decided to do them because it seemed like I could do more problems, more kinds of students would be amenable, they could get jobs, I could do things that would help my colleagues, and so, but I was a newbie. So I'm learning how to do stuff and reading about, different techniques. And one of the techniques I learned about was how you measure solubility of something. So in chemical engineering, you characterize the solubility by talking about the Henry constant, right? Basically, to a physical chemist, the free energy of something from the gas coming into the liquid. And it could be even the same molecule, in which case you're talking about the vapor pressure. Basically, what's the free energy to take a molecule out of the liquid into the vapor? And as I just said, that solvation determines vapor-liquid equilibrium, which is, of course, an important thing. And how could you possibly, well, and so I should say, that's a free energy, not just an energy, because the solute can change the way that the solvent arranges itself. So for example, a nonpolar solvent in water, the water tends to restructure its hydrogen bonds around the solute, not wanting to give up those bonds. But of course, that means that there's less entropy because it has fewer ways of choosing how those bonds are arranged. And so as soon as you're talking about entropy, then you're talking about something which is not just a function of where everything is, right? You can't look at a snapshot of a liquid and tell what the entropy is. You can tell what the energy is. You can even tell what the pressure is, the temperature, but you can't tell what the entropy is. And so simulations are basically ways of making movies of liquids. And so they're really good at measuring anything that you can measure that's just a function of where everything is and how fast it's going, which doesn't include the entropy, and therefore doesn't include the free energy. And so you need special methods to measure free energies. And that's the challenge from the simulation point of view. So what about this Henry constant thing? How might you measure that in a simulation? Well, one way would be, this is not the way people typically do it, but a way would be if you imagine slowly dragging the solute out of solution, and there's an interface. So you can do it. There's vapor up above or vacuum. When it's in the liquid, it doesn't care where it is. But when it gets up to the interface, it starts to care. If it likes the liquid, there'll be a force downward because it's resisting being removed. And that force will persist as you drag it through the interface. Imagine you're doing it slowly. You hold it at some point so you can measure that force, which is going to fluctuate in time, right? But you could measure that force at different points. And then when you get it out into the vacuum, it gives up. It doesn't care how far away it is from the interface anymore. So there'll be a little blip of force versus height, which if you integrated it, would tell you the work it took to drag the thing out. And that's the free energy you want. Well, sort of indirectly in that you might argue that that's part of what determines what this force is. But if you're just trying to measure it in the simulation, the important thing is that you're representing the molecules reasonably well so that the force you measure is the right one. Yeah. And so there are ways of holding a particle at a given spot. Basically, you put it in a harmonic potential, and that sort of serves as a strain gauge, and you can measure the force because if it's pulled down, it tends to be displaced from the center of the potential and so forth. So that can be done in principle. It's not what we do, or it's not what is done in the field, which is what I was learning about. What's actually done is something kind of cool because it doesn't take an interface, and so you can do this in periodic boundary conditions, which we like because then your simulation doesn't have edges, sort of. And what you do is you calculate the work to turn off the interactions between the solute and the solvent. So what do I mean calculate the work to do that? Well, if you look at the progressive change of the energy as you scale the interactions away so that the thing turns into a ghost, you can integrate with respect to that scale. And so the scale is playing the role of a displacement, and the change of the energy with respect to that is playing the role of a force, a generalized force. The way I like to think about this is that there's a little magical dial that you can turn that changes the strength of the interaction. And the dial, has the ability to exert a torque on you. If it takes work to change that, if the energy is going up, then you have to apply a torque to turn the dial. But if the energy goes down, it takes a torque to restrain it. And so if you integrate the torque through the dial, then you get the work needed to turn off the interaction. And if you've turned off the interaction, I mean, the ghost can go anywhere. You've basically taken it out of the liquid. Did you? It absolutely does. The reason it takes up space is because of the repulsions with the other molecules, and you're turning those off. And it fills in the hole. As you turn off the interactions, the liquid fills in the hole, structures in a natural way, and all of that is part of the change in the energy as you turn the dial.
But then you change pressure, right? You have with the hole inside.
Um,
Down with the size of the system, I guess.
You do these things in NPT conditions so that the size of the system might change slightly so that you're not leaving a void. Or if you did it in a big enough box and you make one solute go away, it doesn't matter.
But would you say it's fair to think of that method as the chemical potential? Because if this is a ghost, there is no particle, and then you're gradually inserting a particle. If the interaction is fully
it is related to the chemical potential. Everything is there except translational contributions, because nothing about nothing about the space over which the ghost or the molecule could run around comes into it. All, yes. I mean, well, right, but I mean that's exactly what this delta G is. Yeah, so yes, you can say it that way. In some way, I find it easier to think about it as the work and then to say, oh yes, and that's delta G. But yes. So that's an existing method. That's a standard thing. Simulators use that for measuring solubilities and Henry constants and so forth of single solutes. But suppose you want to know about chi for a polymer blend. Well, so that leads me to the first of 4 methods that I'm going to try to tell you about of how one can try to find out about chi. And it's what I call morphing method. So remember my dial. Imagine that you could transform half of the chains in a simulated melt from one kind of chain to another in a continuous way. So as a specific example, let's consider a mixture of chains where there's half of them are flexible and half of them are more stiff. But they start out life, all of them are flexible. And I could choose at random half of them that I'm going to make stiff, and I turn my magical dial, and they gradually become stiff. And as they do so, I measure the average change in the system energy with the increase in the stiffness parameter. I'm calculating the work to transform half of the chains from being identical to the original to being different. And this is nice because all of the intermediate states are very sensible sorts of blends of, a chain of the initial flexible kind with something that's a little more stiff. As opposed to, for example, if I thought about trying to find out about let me finish that story. So if you compute the work to turn half of them in a blend to the stiff kind, and you compare it to the work to turn all of the chains in half of the system to the stiff kind, if they don't like to mix the flexible and the stiff, then it'll be a little more work to convert them when they're mixed up than when they're pure. That makes sense? And if you take the difference, you can find out about the excess free energy of mixing. A different way of doing it would be, if you want to know whether chains want to mix, what you do is you boil the thing to a gas, mixed versus pure. And if it was a little bit easier to boil to a gas from mixed versus pure, well, then they don't like to mix. but you're taking an enormous difference of free energies, you know, the free energy to boil the thing here and here and ask, well, you know, how different are those? That looks not like a good idea because it's, you know, you have to measure those things extremely finely. Whereas computing this work here, you don't go to some unreasonable state. You're always in some nice mixture. So this seemed like a good idea. And just, you know, in terms of the math of it, what I've been talking about is this equation here. D free energy d lambda is the average energy d lambda is the average force. The dE d lambda is a force. It fluctuates. Take the average. That's the thing which if you integrate with respect to lambda, that's the position on the dial, will give you the change in the free energy. So that's the derivation. And this is just pointing out that taking the difference thing really corresponds to a sort of thermodynamic cycle. So if you go around this cycle, you know, when the chains are the same, then you can mix them, okay? And then if you convert half of them to, you know, to the new kind over here versus over there, then the difference between those is the excess free energy. So chains of different stiffness don't mix perfectly. And that's just entropy because the beads of the chain are the same. So we did a simulation with a system of about so big where we have you know, an angular interaction to make this bead spring thing have an adjustable stiffness and therefore an adjustable persistence length. We go through this whole exercise that I described, and we get this nice sort of landscape of what chi is versus the persistence length of the two species. And down the middle of this, they're the same, and then chi 0, because that's ideal. And in the wings, you know, where there's a big contrast because one of the chains is stiff and the other one's flexible, then the chi goes up. And we've, you know, done various morphs along these different lines in order to learn about the shape of this landscape. This was an undergraduate project. This was an undergraduate honors thesis, a very good undergraduate, supervised by Wenlin Zhang, who's now at the chemistry department at Dartmouth. Those chi's are pretty small, 0.02 at the top. And you might wonder, well, how the heck do you know that this is even remotely right? It turns out that there was a prediction about this by field theory methods in the 90s by Glenn Fredrickson and Andrea Liu. This is a real tour de force of you know, kind of field theory type arguing, which has never been checked until now. It works pretty well. And there's a front factor in their theory that they don't know because everything depends on short distance behavior, but the functional form as a function of the stiffness ratio seems to work extremely well. So that's nice. Another archetypical example is chains that would be identical in their stiffness but have slightly different attractive interactions. And so one can do that and do a morphing in which you change essentially the Leonard-Jones type parameters, you know, a little bit. And now we can do a check in a different way. So we extract the chi that way, but now we can do a check in a different way where we actually do a simulation of a system which this theory would predict would demix. And if it does demix and you can equilibrate it, you can measure an interface. And then you can fit that interface to self-consistent field theory with the chi that you thought you had, and it works great. So the chi, by measuring the interfacial width of something that was demixed, winds up being completely consistent with the one that we calculate by the work done to turn one species into the other. Yeah.
What is the mismatch? Is it only the interaction, or is it?
The mismatch is the factor by which we have weakened the BB interaction, and then we're using, you know, what's called Berthelot mixing to tell what the AB interaction would be. Right. And these are, you know, chains of 40 beads long, so, you know, they're not enormous. Anyway, that's the simulation.
Is this for large stiffnesses, or are the stiffnesses rather perturbations to the flexible state?
Right. So these are still flexible. These are the persistence lengths in beads. So we're talking about, you know, 1 versus 3. The overall chain is still certainly Gaussian, just, you know, that it has a persistence length of a few beads. If it gets to be too many, bad things happen, because then you start to get pneumatics and stuff like that. Yeah, that we're staying out of that. Well, so we got carried away with this. And another thing you might wonder about with regard to these bead spring models is the extent to which the chain architecture might affect chi. So you can envision different structures in which you make one of the beads different on one of two chains. These are sort of poor man's polypropylene, right? So there's a side bead every other bead. And so in 3 different cases, we make a second species in which we change either the side bead or the main bead or the branch point bead to be a little different. Now, any kind of random mixing theory would tell you that I can't tell the difference between those because, you know, there's the same number of red and blue beads and so on. But intuition tells you that those red beads are more accessible. They're more out there. And so this is probably going to have a bigger repulsive chi between those two things than between those, because the red beads are hidden. And so we can do that. And it's true by, you know, something like a factor of 2 or 3, that's a stronger effect. That also was an undergraduate thesis project. Well, what about real polymers, though? Okay, so somehow we need to morph one kind of polymer into another kind of polymer and compute the change of the work needed to do it. But that sounds hard. How do you morph, you know, polyethylene into PEO? Well, sort of like this. I mean, that's just a picture, okay? So how do you do that? Well, what describes those interactions is a great big list of you know, parameters of what are the bond stiffnesses, what are the angle stiffnesses, what are the Leonard-Jones, you know, parameters, what are the partial charges, blah, blah, blah. So it's just a basically big table of numbers. If you allow yourself to have, for example, hydrogens on the PEO that are just ghosts, they don't have any interaction with anything, but they're still there, right? Well, then, you know, you can map one of them to the other by just changing these numbers. So there's a dial, it changes all the numbers proportionately from the first, you know, the first thing to the last thing. So you can do that. And if the structures of polymers are similar enough so that it's not incredibly tedious, you know, then you can actually do chi for real polymers. So PE and PEO, or polystyrene to poly-2-vinyl pyridine, where you turn one of those carbons into a nitrogen. It's helpful if you're using united atoms, obviously, because then, you know, you're not having these hydrogen atoms that are ghosts. Polyisoprene and saturated PI. These are progressively more challenging, partly because the chi's are getting smaller. Okay, and so we played around with that, and you get values that are not crazy compared to experiment. With the PS-PVP, you need to take account that the background dielectric constant isn't 1, because those things are polar, it turns out, so that makes a big difference. And these are clearly getting harder. I mean, the PI, saturated PI, those guys are really small, and the smaller it is, clearly the harder this is to do. And eventually, you realize you can't do dissimilar polymers because you got to grow one structure and then make it disappear and grow another structure, and it's just kind of a nightmare.
The result you get depends on how you choose to dye your, the path of morphing that you choose. Did you check that?
That is not a stupid question. We did not check that in any systematic way. We assumed that that was true. Yeah, no, that's absolutely right. Basically, you have to do it slowly. You got to do it slow, and slow means that you give plenty of time between each little step of the turning of the dial to let the system re-equilibrate. And the way we did it, just as a practical matter, was to use the last frame of the previous simulation as a starting point for the next one and throw away a certain amount of the data. And you make enough steps that things aren't changing very much from one to the next. But so what we did to quote unquote ensure that was just to make sure that the averages we were taking really were kind of time independent, and that the curve of the integrand was not jumpy. So
But this is true unless you have some kind of homotopy or topological states in the liquid.
well, yeah, right. So well, okay, so I mean, yes, that's true. And the other things we do is we simulate hot, so that things move around, and we choose chains that are fairly short so that they're not entangled, so that it doesn't take forever for stuff to move around. And notice the whole thing is done in the miscible regime. Okay, you cannot do this if stuff is demixing, because I mean the whole thing is constructed around around a description of miscible states of single phase. So if you do those things, then then we think it's okay. Yeah.
Another question, when you have ghost particles and you switch them on, even with very weak interaction, there is a divergence.
Yes.
How do you handle this?
We handle that in two ways. One is by integrating the divergence, because it's integrable. And that is, you just take points close enough together that you can see what the divergence is, and you integrate it. The other is we borrow from the people who did the solubility parameters. They have tricky ways of making the potentials soft, and so you can turn on some softness to avoid that problem. Yeah. Okay. Well, so this is nice, but then somebody says, well, what if we want to do this polymer and that polymer and they don't look like each other? And so coming back to the comment that, this is about a sequence of ideas and where do they come from? So we did this and we go, oh God, it gets harder when you do a different polymer. What are we going to do? And so, I don't know, in the car on the way to work or in the shower, I don't know, probably one of those two places, it occurred to me, well, what if I just progressively turned off the interactions between polymer A and polymer B? I made them not see each other progressively. And then I thought naively, well, you'll get to a state where A and B are just cohabiting the same box, but they don't know. Each one is, as it were, a ghost to the other. There was a movie about that. It was like this family, they thought they were being haunted, but actually they were the ghosts and they were the one that were doing the haunting. So I thought it'll be like that, and then they'll be, they won't be quite dense enough in the box because just sort of they're about half as dense as they should be, but I can compress it at the end and find out. Oh, that's great. Let's try that. And then this happened. As soon as you weaken the interactions a little bit, they demix, because because now it's it's a like prefers like type situation, right? So it's like, oh, well, that was stupid, but it's not stupid because you've almost got them demixed, and all you have left is an interface and that interface has a tension. And so, but we know how to measure liquid-liquid interfacial tensions because it pulls on the side of the box differently than, than on the top, right? A liquid interface would try to make the area smaller. And so you can tell that because the pressure on the sides is less than the pressure vertically. Great. Let's try that. So here you can, have the work to weaken the interactions. You can measure the cost of the interfaces, and as you make the interactions more disparate between the two species, both of those things go up in such a way that the appropriate sum of them cancels. I mean, so that the work to demix is now independent of how far I've turned the dial beyond a certain point. Okay. And so we tried that out first with basically with ideal mixtures, okay, in which case we get exactly the answer that you want, which is KT log 2, right? That's just the entropy, because here now we are computing the full free energy of demixing, not just the excess, right? Because we're actually computing the work to make the thing demix. And then we did the same thing with benzene pyridine as a liquid, and you get rather different answers depending on whether you use an atomistic or united atom potential, and that's because the atom potential is not very good for this liquid. And so we did this for a variety of the polymers that we'd done before and got results that were consistent, very happily so. And the beauty of this method is, well, you can do anything, right? There was nothing about similarity of structure that was required. Okay, so that looks great. And we thought, well, we're going to use this for something really ambitious. We're going to use this for, donor acceptor polymer blends that were, relevant to the talk I gave, before. And then this happened. Those molecules are stiff and they structure like crazy at that interface. And that's real. And it makes it really hard to measure that interfacial tension. Box is just not big enough to think of that interface as being here with a whole bunch of bulk fluid over there. The ordering that you induce runs all the way to the end of the box. We just can't make a system big enough to do that. So that was a bust. And we really wanted to get this caught. Now we're stuck. Well, you know the answer because I told you the method that we used already, but where did it come from? So another thing that I was interested in was osmotic pressure simulations, and this for a different reason, because in various stuff that we were doing, we were simulating systems where at least locally the concentrations of ions were big. So aqueous solutions in which you had, some multiply charged thing that was gathering counter ions all around it like bees to a flower. And you want to know that your simulation of those ions in water is realistic. So what does realistic mean? Well, realistic means that they don't clump together with the opposite charge ion too much or too little. And that means that they're, a way of checking that, or something that's quite sensitive to that, is their osmotic pressure. So the standard way, so here's an example of something where you care about that. That's a cavity in a membrane that's self-assembled, that's got sulfonates on the surface of it, and the sodiums are the counter ions, and they hover around the surface a lot, and you want those simulations to be meaningful, right? So or another example is the double layers that you get in electrochemical cells. They're very concentrated. I mean, it's 3 or 4 molar next to the wall if you put any kind of reasonable charge on those plates. How does one measure osmotic pressure in simulations? Well, the method that was in the literature is cute, but actually kind of nasty. You confine a salt solution between some kind of plates. Here, these are pretend graphene sheets that are magically invisible to water, because you can do stuff like that in simulations. And then you measure the force on the sheets to hold them in place with the ions in there. But it's ugly because you can't make it very big, and the ions structure near the wall, so you certainly don't have a uniform concentration in there. And even once you decide what concentration you're measuring the pressure of, which is the one in the middle, you did a whole simulation and you got 1 point on the osmotic equation of state. So I was inspired by a problem I set to my thermo class, the problem of calculating the concentration of colloidal suspension in gravity, right? The normal way of doing that is to say, well, your probability of being a height z above the surface is e to the minus beta, the gravitational potential. But a fancier way of doing it is to consider each slice of the osmotic solution and say, it's in equilibrium between the downward force net, net of buoyancy, and the slight difference of osmotic pressure below, which is a little bigger, and above, which is a little weaker. And those things balance. Well, in a simulation, you could put a harmonic potential on the ions and gather them in the middle, and then you'll get some sort of concentration profile for the ions, which can be analyzed in a similar way, slice by slice. If the ions were an ideal solution, you'll get a Gaussian profile. But if the ions were tending to cluster, it'll get concentrated in the middle, and if the ions are tending to repel each other too much, for example, hang on to their solvation shell too tightly, then the concentration will be flat in the middle. And these things will show up when you calculate the pressure as a function of concentration, which you can do slice by slice in this profile that you've created. And it turns out that the stock potentials for sodium and chloride from OPLS give an actually rather crummy representation of the osmotic pressure when you get up above 1 molar or something, and that's bad. Basically, the sodium and the chlorine stick together too much. And so a way of adjusting that is to just make them ever so slightly more repulsive to each other short range, and then you can just hit the osmotic pressure bang on. That was an undergraduate honors thesis as well. Well, once you start thinking about, and I should emphasize that in doing this, you have to apply this potential not to the center of mass of the ions, but to every single ion, right? Every single ion has to feel this force independently. So that's 1,000 such pulling potentials, as they're called in the thing. But write a script and you can generate the file needed to do that. And then you think, oh, well, if I can do that, then I can interrogate whether a liquid wants to demix or not in a similar fashion. I can apply equal and opposite potentials on every molecule in a mixture. And I mentioned benzene and pyridine, and that's kind of one of our favorite regular solutions, right? And that's what it looks like, right? Those are the pyridines and those are the benzenes, and the little blue things up there are the nitrogens. The funny little kind of liver-colored things are pretend atoms that are representing the quadrupole. So that's not an actual atom. That's just a little charge center that's sitting above and below the ring to make a quadrupole. And so you can see you induce a concentration profile, and what you can do to analyze these at least qualitatively is ask, how does that concentration profile compare to what you would have gotten if you'd used red and green benzene? In other words, benzenes that just had a label, they're chemically identical in the simulation, but you pulled on some of them and you pushed on the other ones. And so the profile where you pull on the pyridine or the benzene versus pulling on the ideal system is a little bit more enhanced. You get a little bit bigger purification, if you want, than you did when they were just pure. And that means they don't like each other that much. And if you give them an excuse, they'll separate more. They're not immiscible, but they're heading in that direction. This amounts to measuring the transfer chemical potential, the exchange chemical potential, because what you're doing is putting an external potential on the system that distinguishes between the two species, putting the thing out of equilibrium. And it responds by rearranging the concentrations in such a way that the chemical potential is back to being constant. So you can actually express this as measuring the chemical potential versus concentration over a big range, all in one go. And that's nice. And it's very convenient, except for the part about having to write a file that has, 5,000 pull codes in it. And it's efficient too. There's nothing, I don't have to integrate anything. There's nothing fancy about it. All you have to do is run long enough to, for the equilibrium profile to be established and measure it accurately, because it's the entire free energy of mixing that you're getting here again, not just the excess. So if in a system like this, it's relatively simple because, that it's small molecules, but for polymers, I mean, then you got to work harder because a lot of you're trying to get chi, and chi is could be a small perturbation on the system. We know what chi is for benzene pyridine because we can fit vapor liquid equilibrium data to get it. What is the excess pressure doing as a function of the fraction, and we get somewhat reasonable values when we use the all atom simulations, terrible values with the united atom. And that's just a failure of the potential. I mean, that just emphasizes that the simulation has to be representing the interactions of the molecules correctly for this to work. And if it doesn't, it won't work. And that's not a failure of the method, it's a failure of the potential. For polymers, well, you can do the same thing. And the only issue is that square gradient terms can contribute to the local chemical potential. You normally don't think about it like that. You just think, well, the local chemical potential just cares what the concentrations are. But if you've worked with self-consistent field theory, you know that the functional derivative of the free energy with respect to the local concentration has second derivatives in it. And those matter because we can't really make our boxes big enough that they don't. But you can measure those coefficients and include them. And when you do, you can do a decent job of getting the chi per bead of some of these bead spring systems from pulling and morphing and ghosting all about the same size. So it's nice that we had those previous methods because we can now compare and make sure we're not messing it up. And that's simulation versus simulation. So there's no you can't say the potentials are wrong. It's the same potentials for all three simulations. And as I said, we can do that even for big stiff molecules because now we're not making any interfaces. We're just making a little wiggle in the concentration profile. And that doesn't induce any order. And so we can actually get a chi out of that, which, as I showed you the last time I talked, gives an interfacial width that's reasonably consistent with the actual interfacial widths of the demixed systems. Why didn't we think of that to begin with? I mean, that's such an obvious and simple idea. Well, we didn't. But what I've tried to show you is, what the progression of ideas actually were and how each one, sort of ran into a dead end and needed a new idea. And, a new idea eventually came along. And in retrospect, it all looks planned. But of course, it wasn't planned. That's just how it works. And sometimes it's nice to kind of reflect on that in your own work and sort of think, well, how did I get here? What was it I was thinking about that made me do that thing in the first place? Which I find myself tends to get erased by the improved understanding. Like it's hard to remember what you were thinking when you had that idea, the imperfect state of, grasping for some understanding. Once you see it, it's very hard to unsee and to remember kind of where you were at. And so I've tried in this particular case to remember that and to share that as part of the story. So conclusions are sort of obvious. Predicting chi is important and it's hard. And simulations, I didn't emphasize this in the beginning, but it's very tempting that simulations would be what you would use to do this, because all of the nooks and crannies and impossible packing choices that an analytical theory, I mean, is just going to fail utterly on unless you're talking about round particles. I mean, the job of analytical theory in making decent equations of state for real molecules is an utter failure, except for Leonard-Jonesium. I mean, and hard spherium. I mean, other than that, forget it. So simulations are great for that, but because you need free energies, it requires special methods, of which I've described several. And morphing works well as long as the structures are similar, and the statistics on that are great, right? Because you're getting this information from every single molecule in the system, and it's only the excess free energy, right? So that's really good, but you can't really do that for the sort of chemically disparate things. Mutual ghosting is cute and works well even for disparate structures as long as the liquids are flexible. And pulling seems to be, simple and robust. So, that's where I want to stop. And I thank you for your patience. I've gone a little bit longer than I intended, but I hope it's been reasonably entertaining. And I'll take any further questions.
Yeah, thank you very much. Very nice. There are more questions. Yeah.
Can you use some of your methods for reverse engineering? Because of course, I mean, the dream is if I know what kind of crazy demixing behavior or nonlinear behavior I would love to have in a mixture, could your methods be useful to turn them around and rather say, okay, if I want to have this crazy behavior, what kind of morphing path, like where do I need to morph to or pull to or ghost to or whatever is the right vocabulary to tell me what are the kind of polymers, molecules that I need to design to get that behavior?
In a word, no. I mean, of course you want to do that, but I mean, what you're asking is there something special about this approach where you can tell me what structures to make in order to get the chi that I want? And that doesn't have anything to do with the morphing path or the ghosting method or the pulling or whatever. I mean, those things can be used to check to see whether your guess as to what kind of structure would give what you want is a good one. But they can't generate guesses for you in any way that I can see. I mean, I'm old school and very admiring of, synthetic chemists who seem to have amazing intuition about what they ought to make to achieve what they want. And what's weird is when you ask them, why did you make that? What comes out of their mouth is often nonsense. I mean, and yet they know. I mean, that's unkind. That it doesn't sort of pass muster as a theoretical explanation, yet they clearly have some idea in mind. And I think that is our best, physical understanding of where the interactions come from, and intuition about what to make is still our best guide for that kind of thing, and we should treasure it. I mean, people who are good at that are amazing. So yeah, no, there's nothing here that makes that not necessary.
Thank you for the talk first. I think you showed a schematic where at the interface, when you had a somewhat stiff polymer, it would structure particularly at the interface. Right?
Here?
Yeah.
Yeah.
And so my question is, if you have somewhat or much stiffer polymer mixed with a much well, less stiff polymer. Could you predict that the more flexible polymer gets organized, structured by this?
Right. So
labor at
that's
the
kind of a
interface?
general question. I mean, imagine that you have, immiscible polymers and for whatever, and one of them is more stiff or one of them is more flexible or whatever. I mean, viewed a polymer of a given stiffness up against a flat surface of any kind will tend to lie parallel to that surface. I mean, it has to, because it can't, point toward the surface and then make a sharp U-turn in order to avoid going into the wrong phase. I mean, so they have to lie flat. And then even if that polymer isn't pneumatic in the bulk, in other words, isn't, so stiff that it spontaneously develops, a local agreement about the direction, that interface will induce pneumatic order and locally. And so you will see over a range of a Kuhn length or so, persistence length of the chain, away from that interface, you'll see pretty significant alignment. And that's a generic thing. And how big an effect it is, of course, depends on how stiff the chain is, because I just said that it persists out over a couple of persistence lengths. And it's possible to make predictions of that kind of thing with versions of self-consistent field theory, for instance, that include not only the concentration, but also the orientational order in the theory. And there's various folks that have worked on that, including us. And you can see that kind of thing in simulations too. So that's generically what you expect.
So you mentioned this field theory by Andrea Leo, and field theories have some tendency to be a little bit hard to interpret visually what the parameters there mean. But do you have a simple physical picture? What does it mean, stiff and soft polymer? Why do they mix? Is it because of the particular anisotropic shapes that they have, and they kind of a mix like because of the shape, or maybe some kind of shear fluctuations have maximal entropy if there are more mixed, like in membranes, you have stiffening, etc.
Talking physically about entropy is always hard. If I want to try to give a reason why stiffer chains and more flexible chains would have a tendency to demix for entropic reasons, I guess what I would say is the stiff ones, have lower configurational entropy per monomer. That is, they're tending to run straight, okay? And they are relatively happy to be up next to other ones that are also doing that. There's no wasted space in there. There's no wasted freedom, so to speak. It's not pneumatic, but locally somewhat aligned, and they're all kind of happy. A chain that's flexible is happy to be near other flexible ones. It's greedy for configurational entropy. But a stiff chain next to a flexible one, the flexible one is constantly running into, not constantly, but anyway, tending to run into a wall, so to speak, on a short scale. And this it does not like. And I think that's the, if I'm making this up, right? Okay, that's my hand wave about why this is. It's packing entropy. That's not a very helpful statement, but that is my physical, that is my mental image of why it is. It's
basically shapes, and they're a little bit squishy, and you pack them next to each other.
Yeah,
More
without giving up local conformational entropy and without having holes. Those are the requirements. Yeah.
Thanks.
First, thank you for the very interesting talk. And my question is, there is some out of equilibrium method inspired by Jarzynski work, where they do not quasi-static change of your lambda parameter, but on a finite period. Did you try to adapt your method to this out of equilibrium or finite time procedure? And if so, what is the outcome?
So the short answer is no, we haven't tried anything that's not quasi-static. That is a more general question. That is a more general question of, well, you might say computational efficiency, for example. Well, okay, suppose I want to measure a potential of mean force between a particle and another particle, or between a particle and a wall, or something like that. The conventional way is to set up a set of umbrellas that are, at different distances from the wall, and simulate in each one, and measure the force and integrate it to get the potential, and so on. The Jarzynski way, as I understand it, is to slowly, but at a finite rate, drag the particle away from the wall, and then to use some, well, it's not magic, of course, but it seems somewhat magical, some statistical magic to measure, to convert what you see into something that doesn't have any sensitivity to the friction that you clearly had when you dragged it. I have not investigated that comparison of methods in publication, but I have thought about it, and it looks to me as if to get reasonable statistical accuracy in the Jarzynski method is very challenging indeed. It's a little bit like Whittam sampling, that you're fighting an exponential factor which is making the events that dominate the thing you're measuring extremely unlikely. And this makes it difficult to do Jarzynski with high accuracy. And so that the question that I've kind of set myself at one time that I thought, oh, this would be cool to answer, and I never have, is if I had a finite amount of computational resources, and I compared, in a scaling sense, the accuracy that I could achieve in the PMF as measured by, conventional umbrella sampling versus Jarzynski versus other things that you might think of doing, who wins? And I don't know the answer to that, but I think that would be a good thing to do, because it's quite generic, that question, and it's not something, as far as I know, that people have said.
Thank you. Very nice discussion about Jarzynski. Thank you for showing all these nice tricks and very, very clever ways of computing chi. I have the feeling that in the end, you say that you can measure chi from reading the density profile, right? And I think that there is probably an assumption of incompressibility,
Yes.
or equal compressibility of the two
Yes,
phases. And do you think it can alter, or are there systems where you should be careful about it?
That's a good question. Yes. So right. I mean, the examples that I've focused on the most, well, first of all, most systems of interest that we're interested in have very small volume changes on mixing. And so what I think is the right thing to do is to focus on the concentration of volume elements, right? Not mole fraction, not mass fraction, blah, 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 but volume fraction defined in some way where you say, look, this monomer takes up this amount of room, and I measure how much room it takes up in its own pure phase, and then I'm just, by golly, going to assume that that amount of room is the same in the mixture, and it pretty closely is. You can check those things after the fact. And then to just formulate everything in terms of volume fraction. That clearly is the right thing if you've got, beads that are, chains that are stiff and flexible. That's obviously the right thing. It's pretty clearly the right thing for a regular solution like benzene and pyridine, where those two molecules take up basically the same room. But I think generally speaking, the safest way to analyze these results is assume incompressibility, assume zero volume change on mixing, and do it like that.
But then for what you are talking about, ions and the hydration shell, this would be clearly quite wrong, no?
Well, I'm never going to look at salt crystals here. I'm only looking at solutions of ions with different concentrations of the ions. So the volume that the ions themselves take up is, if I blend a salt solution with pure water, and I say, well, what was the volume that the ion took up in the solution, and then what's the ion it takes up in a more dilute solution, those are pretty comparable. I don't want to take a crystal of salt and ask what was the ion doing there versus the water. I'm not, I mean, of course, for a complete description, you'd want that, but all we're really trying to get right here, for example, in the case of the double layer next to a metal, I mean, it's not a salt crystal there, it's 3 molar or something, and out away from the plate, it's 100 millimolar, and you're trying to get that right. So, I mean, anyway, that is how I would approach it until it bit me.
In polymer thermodynamics, the chi parameter is known to be temperature dependent. And so there's a lot of discussion about that and a lot of empirical formulas. You showed chi parameters for one specific thermodynamic condition, but if there's a temperature dependence, how well would your method work?
I don't have the slide here, but in my previous talk, I actually showed that we measured chi for several different temperatures for the P3HT IDTBR system, and indeed fitted it to the A plus B over T type form, and you can say the usual words that people say about one of that, part of that being entropic and part being enthalpic and so on, but in practice, that's what we did. These comparisons, these are single temperature values, and the curves are coming from the experiment. These curves are from the review article of Nitash Balsara and Aituni, right? The compendium of all chi. That's where these come from. We did not try to measure these at multiple temperatures here, but we did do for the P3HT IDTBR system. I might also say, also that of course these chi's depend on concentration too, and that is a thing I'd like to explore with bead-spring type systems, to ask, what are the conditions under which you get linear versus quadratic dependence of the concentration of chi. I need another undergraduate for that. I mean, it's the kind of project that, an undergraduate could actually do, is the thing. And so when you have a project like that, you don't want to waste it on a graduate student.
From the chi parameter, can one predict the interfacial tension, or can one interpret chi as an interfacial tension in the sense that when they fix the mix and how far they are, it means higher interfacial tension, and when they like to mix, it is like more a negative interfacial tension?
Yes. So where was it? The theory, which I didn't put the reference to, but it's Gene Helfand and Tagami, 1974 or something like that. And I mean, that was a beautiful little paper. I mean, just really an early example of using self-consistent field theory to do something really nice. Also predicts the interfacial tension here, because this is a Cahn-Hilliard type profile here, right? This is, a Tanch type profile across that interface of concentration. And so it's possible, and I don't remember how it scales, but it's certainly the interfacial tension goes up as chi goes up. Eventually you run out of steam in that theory, because the interfacial tension would get as thin as a monomer and it doesn't work anymore, right? But in the range where there's some intermixing of the thing, where the chi isn't too big, yeah, absolutely. The the interfacial tension is governed by chi.
Okay. We had a very nice discussion. So thank you again. And if further questions pop up, you know that Scott is here still a week and you can ask him directly. Thank you.